Hey y'all. Okay, so we have done, I have videos for 12.1, 12.2, 12.3. We did 12.4, 12.5, 12.6. And if you notice that big capital, probably can't see it where it says mess up at 12.7, I actually messed up. So we are going to do that video again. Okay. In 12.7, what we're going to do is divide polynomials. I'm going to explain the greatest common factor for coefficients and variables, and then I'm going to explain prime factorization, and I'm going to explain what it actually means to divide by the GCF. We will do these first three examples, finding the GCF using prime factorization, and then I will do another video actually dividing this polynomial right here and this polynomial right here by the monomial. They're each being divided by a monomial. And then I'll come back to do this one and finish with that question right there. Okay, so let's go back up to the top. Let's hit hide. So I'm going to zoom in to read this a little bit better. Top left, greatest common factor. The greatest common factor, which I will also just say GCF because lazy, is the largest number that equally divides all the terms. If you have two terms, it's the largest number that divides both of those terms. If you have three terms, it'll be the largest number that divides all three of those terms, not just one, not just two, but every single term. So if you look at the GCF for 2 and 4, the largest number that divides both of those is 2. The GCF for 3, 12, and 30, the largest number that divides all three of those is 3. If you look at 2, 7, and 1, the largest number that divides all of those is just 1. It's the greatest common factor. That's the largest number they have in common. So go ahead and scooch on over to the right top box. The greatest common factor for variables is still going to be called the GCF. The only difference is instead of looking at the coefficient or the numbers, what we're looking at is the actual variables. So for example, if we have x cubed and x squared, because the greatest common factor for variables is the one with the smallest exponent, it would just be x. A way that you could do this, it's not very common, but a way that you can do this until it really makes sense to you, we could go ahead and write these out. I would kind of stack them on top of each other, do them like a column. And I know x cubed is x times x times x, right? And then x is just x. And then x squared would be x times x. Now, if I look here, that's the only thing they have in common. It's just x. If your variables have the exponents of 13, 9, 12, 7, no one really wants to write x times 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 x a few times and then find their common ones. So that's why it's easiest, I think, to just remember that the greatest common factor for your variables is going to be the one that has the smallest exponent on it, okay? So let's go bottom left. Whoop, getting away from me here. I had a typo, and I did not feel like copying and pasting again. So here we go. Prime factorization. Prime factorization is also known as the fundamental theorem of arithmetic. The fundamental theorem of arithmetic states that all numbers can be written as a product of prime numbers. So just a heads up here. Prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 37. They keep going up and up and up, right? With prime factorization, we're usually always going to start with 2 if the number we're looking at is even, and you can always start with 3 if the number that we're looking at is odd. Very rarely, unless it's a huge number, which honestly I'm not sure what the homework does for you, but very rarely, unless it's a huge number, would I get to like 17s and 19s and stuff like that. Some people may notice that 1 is not written, and that is because the definition of a prime number, sorry, there's something in my teeth. The definition of a prime number is going to be a number larger than 1 that can only be divided by 1 in itself. In other words, could not be written as a product of composite numbers or two other numbers. So like 2 cannot be written as being equal to 2 and 3 or 2 and 5 or 2 and 7. If you look at the number 35, it can be written as 1 and 35, 5 and 7. Like there's a couple of different ways you could write and get to 35. There's only one way that you could get to 2, and it would be 1 and 2, right? So that's why it would be considered a prime number. Examples of that would be, as far as the prime factorization is if we have the number 27, prime factorization would give me the prime factors of 3 and 3 and 3. That fundamental theorem tells me that I can do 3 times 3 times 3, and I get 27. The prime factors of 30 would be 2 times 3 times 5. The prime factors of 24 would be 2 times 2 times 2 times 3. And I'm actually going to show you a way that we will find those prime factors. So over here to the right, that rule looked kind of small, so I wrote it bigger. If we are doing this, we're actually going to have a polynomial, and we're going to divide it by a monomial. And what I mean by divide is we're going to need to actually find the GCF, and then we'll divide by the GCF. It'll all make more sense when we actually get down to those bottom problems. You'll hear me say pull out the GCF, and that's what I'm saying is figure out what the GCF is and then divide each term by the GCF. So the directions here say divide all terms by the GCF. We're going to use the quotient rule when we can. And the quotient rule is if you have a base raised to a power. So a sub m, a raised to the m power, the mth power, right? Divided by a to the n power. Those are the same bases. Those are both a's. Because they're the same bases, the quotient rule tells me to keep my base and subtract my powers. So you'll notice we'll do a lot of that in a problem in this section. So let me go ahead and find the GCF of problems 1, 2, and 3 below us. And then after that, we will continue with another video. We can cover up examples. We can zoom in a little bit. So find the GCF of the following. Use prime factorization. So whenever I described prime factorization, I'd stated that what we could do was have a number and write it with its prime factors, plural, right? More than one. 2 times 2 times 5 times 7 times 11, right? Like that would be multiple prime numbers. And if I multiplied them all together, I would get the number that they came from. If you look at 2 is prime. If you look at 5 is prime. We don't actually do prime factorization for prime numbers because prime numbers are already prime. Prime factorization allows us to write numbers that aren't prime by multiplying a number of prime numbers, right? My 27 was written as prime numbers, 3 times 3 times 3. For my 2, it can only be written as 2. That's the prime factorization of 2. It's already prime. And for 5, it can only be written as 5. They're going to get a little bit more involved with the other 2 examples, but the step's still the same, right? The prime factorization of a number, and then you look to see what do they have in common. Well, 2 is just going to be 2 because it's already prime, and then 5 is just going to be 5 because it's already prime. They don't have anything in common. So because they don't have anything in common, what we would say is that the prime factorization of 2 and 5 is just 1. 1 is the only number that can divide 2 and 5. Okay, so let's do finding the GCF of 4 and 24 using prime factorization. This is how we do it. We take the number we're looking at, and you're going to do, it's like an upside down V, like a little branch. We're actually going to divide 4 by prime numbers, and we will continue to divide by prime numbers until all we have left are prime numbers. So because 4 is even, I know for a fact that I can divide by 2. When I get 2, that the line I just drew, when I divide by 2, what I get is going to be a quotient, right? That's the answer to a division problem. That answer is going to go right here. So if you do 4 divided by 2, you get 2. 2 is the smallest number in our list of prime numbers. And because 2 is prime, I'm done here. I don't keep going. So what we can say is that 4 can be written as 2 times 2. 2 times 2, right? So now I'm going to do 24. Because 24 is even, I can divide by 2. My quotient goes right here, which is 12. Because 12 is even, I can divide by 2. My quotient goes right here, which is 6. Because 6 is even, I can divide by 2. The quotient that I get right here is 3. Do y'all see how 2 times 3 gave me 6? And then 6 times 2 gave me 12. That's where all of those are coming from. That's why I'm saying quotient, because what I'm doing is 6 divided by 2, and that gave me my 3. And you go about it in this manner until you get down to nothing but prime numbers. Now, if you notice, I have nothing but prime numbers here as well. I have 2 times 2 times 2 times 3. Now, once we have this list of prime numbers, we're going to look and we're going to see what do they have in common. Let me go and write this right here, y'all. GCF of 4 and 24. Okay, so there's 2 different ways to go about this. You can write it with the equal and the list of prime numbers, and we can look and we can say 2, 2, 2, and 2. That's what they have in common. So 2 times 2, that equals 4. Okay, they have multiple common prime factors. You multiply them together, we get 4. There's another way that you can go about this. If you don't want to write the equal and the factors, what you could do is just let me pretend like those don't exist right here, y'all, okay? What you could do is once you have all of everything broken down in that manner, you could do the same thing and look for what's in common. I've got a 2, I've got a 2, I've got a 2, I've got a 2, I had a 2 and a 2, and I got 4. It's really just whatever's easier to you. In the form that we just did in the purple, a lot of the times having this 12, having that 12 and that 6 there can be confusing. People may actually include it in the prime numbers just on accident. And so if you wanted to mark these out when you do the division, you can. Or like I said, you could just list them this way. And then that way, maybe it's going to be a little bit easier to see what they have in common. Okay, so let's do 42, 24, and 30. Definitely I'm going to need a little bit of space here. I know that I want to write my answer here. GCF of 42, 24, and 30 is going to be, because this is where I've been breaking everything apart, I have 42. Because it's even, I know I can divide by 2. And 42 divided by 2 is 21. Can I divide 21 by 2? I can't. It's odd, but I can divide it by 3, and I would get 7. And then 3 is prime, 7 is prime, 2 is prime. Okay, I'm done there. I'm going to go ahead and write this as a product of prime numbers. And then now let me look at 24. I know we just did it. We could do it again. 24 is even. It can be divided by 2. I would get 12. Then I can divide 2 into 12 because 12 is even, and I get 6. I can do division again by 2, and I get 3. Those are all prime numbers, so I can do 2 times 2 times 2 times 3. And then now we need to go ahead and look at 30. Y'all, you could either divide this by 2 because it's even, or you could divide this by 3 because it can also be divided by 3. Just because it's even doesn't mean you can't divide it by 3. If it is divisible by 3, you can divide it by 3. It's however you want to do it. Personally, I always divide it by 2 if it's even, just because I like how it'll go in order. There'll be a bunch of 2s and then other stuff. If you divide by another number, you'll notice they're kind of mixed up a little bit, and it's easy to lose some factors. So I'm going to divide by 2, and I get 15. 15 cannot be divided by 2 because it's odd, but it can be divided by 3, and I get 5. So 30 can be written as 2 times 3 times 5. Also, starting with the division with 2, when you go to write it in this way, you want those to be in order. So it's okay if you don't do it in order here, but that has to be in order. And I don't mean like it has to, because on an exam, if you have it written out of order, it's counted wrong. That's not true. It just has to be in order, honestly, because it's going to help you actually see what there is in common. If you got a 2 in the front, you got a 2-way on the back, you're probably not going to see that first, and it could get confusing. So let's go ahead and let's see, what do they have in common? Well, here's a 2, and here's a 2, and here's a 2. And then look at my 42. The next prime number is 3. Here's a 3, and there's a 3, and there's a 3. Okay. The next prime factor in my 42 is 7. There's not a 7 in my 24, and there's not a 7 in my 30. So let's look at 24. I got 2's left, but I'm already out of, other 2's to circle. Then if you look at your 30, I have 5, but there's not a 5 in 24, and there's not a 5 in 42. So that would mean that the only numbers that they have in common, the only prime factors that they have in common are 2 times 3, which would give me 6. This is saying that the largest number that can equally divide 42, 24, and 30 is 6. Don't get me wrong. 2 obviously can divide 42 and 24 and 30, right? So can 3, because we circled it in all of them. 3 is also a prime number that can divide all 3 of those. But I don't want just any number that can divide all 3. I want the largest number. So that's why it wouldn't just be 2. It wouldn't just be 3. But it would actually be 6 that divides all of them. So that is how you do prime factorization to find the greatest common factor. Some of the problems do get a little crazy with the different coefficients. I truly believe that the more you do it, the more you kind of see some patterns, and the more it's a little bit easier to get the GCF. You won't always need to do it this way. For these videos for 12.7, I will do it this way. But doing your homework, it's okay if you don't do the GCF doing prime factorization, as long as you get the prime factorization, the greatest common factor correct. So hopefully that's just a little bit of hope that this little process right here doesn't have to be done every single time. Okay, y'all, I'll be back. Let me know if y'all have any questions. Okay, thanks. Bye.